Just as linear mechanics has values such as displacement, velocity, and acceleration, rotational mechanics has equivalents like angular displacement, angular velocity, and angular acceleration. The first of these values, angular displacement, is the angle through which any point in a rotating system revolves, and is usually measured in radians. It is a vector quantity, with counterclockwise rotation being positive and clockwise rotation being negative. This convention exists due to the numbering of the quadrants on a graph. The values increase in the counterclockwise direction. We can find the arc length s through which a point in a circle travels using s equals theta r. This means not all points in a circle will travel the same distance for the same angular displacement, as their distances from the centre of the circle will vary. The angular equivalent of linear velocity is represented by omega, and is angular displacement divided by time. These two equations can be used to link linear speed to angular speed. Linear speed will be the arc length travelled through, s, which shouldn't be confused with displacement, divided by the change in time. Since arc length equals theta times the radius, we can sub it in to get speed equals theta r over change in time. Then the equation for angular speed can be rearranged to make delta t the subject. Delta t can then be subbed into the equation we have for linear speed to get v equals omega r. Angular acceleration is denoted by alpha and is equal to the change in angular velocity divided by the change in time. There is, however, another type of acceleration which occurs even for objects travelling at a constant angular velocity. This is because the direction of the object is constantly changing, so it must be accelerating. This is called centripetal acceleration, and it acts towards the centre of the circle. The magnitude of the acceleration is given by the equation a equals v squared over r, and will always be positive as the v term is squared. We can prove this equation using vectors. The diagram shows an object travelling in a circular path with its position vector r and velocity vector v at two different points during its orbit. The magnitude, speed of v1 and v2 will be the same, and the magnitude of r1 and r2 will also be the same, as this is a circle. We can form an isosceles triangle using the two velocity vectors and angle theta. The angle between the two vectors is theta, as v1 is at 90 degrees to r1 and v2 is at 90 degrees to r2, so the angle will be the same as that between r1 and r2. The last side of the triangle is equal to the change in velocity. We can then form the segment of the circle enclosed by r1 and r2. The curved side will be the distance travelled along the circumference, which is just velocity multiplied by the change in time. Now, since we want centripetal acceleration for the smallest time frame possible, we can let theta tend towards 0. As this happens, we can let v delta t become the straight side of triangle 2, as the curved length will get closer and closer to the length of the chord. We can then compare triangles 1 and 2. They are both isosceles and share the angle theta, so they are similar triangles. As a result, the ratio of v to r, the longer sides of the triangles, is equal to the ratio of the change in velocity to velocity multiplied by the change in time on triangle 2. We then multiply both sides by v. Delta v over delta t is just equal to the magnitude of acceleration, so we can replace it with a to get our final equation. I also mentioned that centripetal acceleration acts towards the centre of the circle, but why is this? If we consider the same circle again and again let theta tend towards 0, v1 and v2 will be so close to each other along the circle's circumference that they are pretty much acting in the same direction. This means the delta v vector will be acting perpendicular to both v1 and v2 as theta becomes very small. Since delta v is acting towards the centre of the circle, the acceleration will too, as a equals delta v over delta t.